That's normal. So we've got the matrix, and what was it again? 4, 1, 2, 3. Okay, and we found, Sean, what were the two eigenvalues? 5 and 2. Okay, so we found these eigenvectors by looking at that characteristic equation. Okay, what was the eigenvector corresponding to this eigenvalue, Martha? 2, 1, or any scalar multiple of that, and the S1, S2. The eigenvalue corresponding to this, Marie? Minus 1, 1, or 1 minus 1. It doesn't really make much of a difference there. Okay, so what this information is telling us, the whole point of an eigenvectors and eigenvalues is that if we do the matrix 4, 2, 1, 3, and apply this eigenvector here, 2, 1, it's exactly the same as having lambda, which is 5, and 2, 1. That's what it's saying. And similarly, if we have 4, 1, 2, 3, we apply this eigenvector, minus 1, 1, it's the same as the effect of multiplying it by 2, minus 1, 1. And my question to you is, we've got two statements there, 1 and 2. How could we write them as a single statement? We've got two equations there, two truisms, if you like. That's true and that's true. How could we write that as one matrix equation? Any ideas there? You've got to think about matrix multiplication. Check on a bit of coffee now. I mean, look. Let's just play around with this. 4, 1, 2, 3. Let's first of all apply this vector here. 2, 1. Okay? And if we multiply it, we get 4 times 2 and 2 times 1. And that will give us our top number. Okay? And let's also apply it to minus 1, 1. So what I've done here is I've taken my two eigenvectors and I've placed them in the columns of this matrix here. Okay? Now, that is going to be the same as, we've got the eigenvalues there. What are we going to put in this matrix which represents these two eigenvalues? So we've only got two numbers. How could we write that matrix if I have that as the same there? So I've got my eigenvectors on both sides. What am I going to write in that matrix corresponding to the eigenvalues? Charlie? Any ideas? 5 and 2. Where are they going to go? Top left, top right, 0, 0. Is that what you're saying? So let's have a look here, because we are hoping that this is a 2 by 2 matrix when we multiply it out. This is a 2 by 2 matrix. Okay? Our answers on both sides should be 10, 5, and minus 2, 2. Okay? Top left, bottom left. So top left, bottom left. So you're changing your mind. Top left, bottom right. Okay? Because here, what we've got, 4 times, if we look in this matrix here, they should both equal. 5 times 2 is 10. 5 times 1 is 5. 2 times minus 1 is minus 2. 2 times 1 is 2. Okay, this is what they should both equal. If we look at the top column, we get 4 times 2 is 8, plus 2 times 1 is 10. Brilliant. Let's do it here. 5 times 2 is 10, plus 0 times 1 is still 10. Okay, let's do it for this element here. So that's multiplying 1 by 2, which is 2, plus 3 times 1 is 5. Brilliant. Let's do it for this one here. How does it work for this? 0 times 2 is 0 plus 2 times 1 is 2. What mistake have I made? That should be 5. I multiplied the wrong ones together. I'm going to get a minus 5 there. Are these the correct Are these the correct eigenvectors? It shouldn't be any different. Should be the other way around. Sorry. Should be the other way around. So that would be 2 minus 1, 1, 1, and 5, 0, 2, 0. We get 2 times 5. Remember, these should both. So 2 times 5 is 10 times minus 1 times 0 is still 10. Good. This element is 5 times 1 is 5 plus 0 is 5. Good. Top one here, top one there. 2 times minus 1 times 2 is minus 2. Good. 0 plus 1 times 2 is 2, as it applies. Okay, so I got them the wrong way around. Okay. So we've converted the 2 bits of information here into one matrix equation. Now if we let's call that M, okay, and I'm going to call this matrix, our eigenvectors we denote by little s, so I'm going to call this matrix capital S, this is also capital S, and this is multiplied by this matrix formed by the eigenvalues going along the diagonal. Now I'm going to call this matrix, I'm going to call it a big thing like that, and that's a bit, that's not meant to be on the hook, but now, what is M equal to then? This is a matrix equation. Whatever we do to one side, we do to the other. We want to get rid of this multiplying by S. So what do we multiply it by on the right-hand side? What do we multiply here to make that S go away? The inverse of S. Now, matrix multiplication isn't commutative, so we have to be really careful with the order. Because effectively, we're multiplying by the inverse of S there, we have to multiply by the inverse of S on the other side as well. Okay? So what we end up with is that M is equal to S multiplied by the matrix formed by the eigenvalues multiplied by the inverse of S. And we say, by writing M like this, we are diagonalizing the matrix. Okay? Why do you think we use the word diagonalizing? Sean? Yeah, this matrix here, the eigenvalues are diagonal. This matrix is a diagonal matrix. It's got 0 entries, pardon me, in the other columns. Okay. So what we need to do now is to find the inverse of S. Now for 2 by 2s, this is quite straightforward. S is, what did we make S to be? S is this matrix here, formed by the columns of the eigenvectors. Now the order does matter here. My first eigenvector, value 5, means that my first column should be the eigenvector corresponding to 5. Okay, so the order does matter here, otherwise you get it all completely wrong. So what was it? 2, 1, minus 1, 1. Okay, so determinant of S, 3. That's not a problem. Determinant of S is 3, 2 times 1 is 2, minus 1 is 3. So the inverse of S, remember, that is going to be 1 over 3. Anybody remember the 2 by 2?
1, 1, minus 1, 2.
That's
Go
it.
across.
Okay, yeah, it is. Can you explain how you did that?
So you swap A and D and change the signs of B and C.
So swap those two, change the signs of A and B. Good. So there's the inverse of S, which is a third minus a third, 2/3. So M is equal to 2, 1, minus 1, 1, multiplied by 5, 0, 0, 2, multiplied by a third, minus a third, 2/3. Okay? Why have we done that, might you ask? Is that what you're thinking, Sean? Why? I mean, look, we've got diagonalising the matrix. We've got a matrix here, perfectly good matrix. You know, 4, 2, 1, 3. There's nothing wrong with that, yeah? And now we're writing it in a form where there's 3 matrices multiplied together. What's all that about? Okay? Now the beauty is, let's examine that equation again. S inverse of S. Let's say we want to work out n to the power of 4. Okay? Now n to the power of 4, we'd have to multiply n by itself 4 times if we didn't know how to do this. So this becomes S multiplied by S. I can't be bothered to put lines there. Okay? Make sense? Now, how does this simplify? Well, those matrix multiplication, the order does matter. Those are just going to disappear. Inverse of S multiplied by S is going to disappear. Those two are going to disappear. And those two are going to disappear. Yeah? So a lot of that disappears. What we're left with is that n to the 4 is equal to the S there. Now we've got 1, 2, 3, 4 of them to the power. So it will be that matrix to the 4. And we're left with an S to the minus 1 there. So in terms of our things, S is 2, 1, minus 1, 1. That to the power of 4. Now this is the beauty, yeah? If we've got a diagonal matrix, this to the power of 4 is just going to be 5 to the power of 4, 0, 0, 2 to the power of 4. And then we're going to have it multiplied by a third, minus a third, 2/3. Okay. So now we can do all this. 2 times 5 to 5 to the 4 is 625. So 2 to the power of that. 2 times 625, 1,250. This element here is just going to be 5 to the 4, 625. 2 times 0 minus 1 times 2 to the 4. 2 to the 4 is 16. That would be minus 16. 16. Right. And finally, it's a third of 1250 plus a third of 16, which is 422. Here we have a third 625 minus a third of 16, so 625 minus 16 divided by 3 is 203. Here we have a third of 125 minus 2/3 of 16, so what I'm going to do is I'm going to put 1250 minus 32 divided by 3, that's 406. And 625, a third of 625 plus 32, so 625 plus 32 divided by 3 is 219. So m to the 4 is all of that, which is a lot quicker than having to do, you know, what was it, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. But you do have to find the eigenvalues and eigenvectors in the first place. So once you've found them and do all this, it's quicker. If you've already got the eigenvalues and eigenvectors, otherwise it would probably be quicker. Okay? So that is really the power, and that's what they're going to ask you in the exam. They'll do it in stages in the exam. They'll say, first of all, here's a matrix, find the eigenvalues, find the eigenvectors. Then they'll say, hence or otherwise, calculate n to the power of 6. But because you've already got the eigenvectors and the eigenvalues of those matrices, this becomes quite a straightforward task. I say relatively straightforward, but essentially it's just practicing matrix multiplication. Okay? Any questions with this? Charlie? Well, it's exactly the same theory. Exactly the same theory, but you can, with 3x3s, they're more likely to use what we're going to look at tomorrow, or no, well, we'll see how that comes. The Cayley-Hamilton theorem, which we're going to look at as well, which is again a very high-level topic, but actually quite easy. With 3x3s, it's probably better to do it using the Cayley-Hamilton theorem. Cool. Right, in your books then, page 117. We'll do question 1, part I, just to have a go at doing that. Then question 3, part I, and part II. Okay, so you're going to have to find the eigenvectors and eigenvalues of these. So it's good practice anyway. So that's probably going to take us up to time in those 3 questions. But let's see, I think I was still recording actually.